So, hello everybody. Welcome to the first 271 workshop for the semester. It's gonna be mainly focusing on assignment simulation assignment 2 that usually is given to you after you get a lot of understand or a big understanding on diode circuits. But if you don't understand or haven't gotten to that part in class, it's still understandable to like see it with Multisim. Multisim helps you a lot visualize it in a better way because you get to see the circuit perform. Um, Usually, assignment two is should be fairly simple, just to the principal eye for um, how to get into diode circuits, because then that builds up to rectifiers, which is a big important part with diodes. Um, but moving on from that, usually. And the assignment is just basically based off the book. So, considering the circuit B below, where we are given a value of the voltage on of the diode, um, usually what will be the voltages and currents in both diodes? So, voltage on, which he'll get to explaining in class, is basically the voltage drop across a diode in a circuit when current is running through its anode to its cathode. So usually that gets you a better like it's like basically like a resistor that has a set voltage drop, but it needs a certain current to break a certain voltage to break through it to then have a set voltage. So like in a resistor, usually it's like the best example, like a 1 volt battery source is connected to a 1 ohm resistor. The current is 1 amp. But the voltage drop across that resistor will be 1 volt. In the case of a diode, let's say for the voltage of the diode when it's on, it will have always 0.4 volts when it is in the forward active region, which is on. It's going through the anode to the cathode. Um, so usually this kind of goes into like a bit more in depth with math, but it's not too serious that much. So to tackle this problem, we're looking at this circuit of like in this configuration. So how to solve it? Um, Usually he'll also explain about assumptions. You take different you as many assumptions as you can to get a proper solution. So analytically solving this circuit, we would usually choose to have if the first diode, which was the one that was here, is on, and the second diode is off, which will behave as an open circuit. So when the diode is off, it won't have any current running through it. Behaves like if it's an open circuit, like there's no connection and no current is going to run through it. But a voltage will build up between the terminals of the anode and the cathode. Um, so going back to the previous or the first diagram, we usually see that here it would be like um, this would be the positive end of the voltage drop, and then this would be the negative end. Same thing for this one. It will be positive here and the negative. So the assumption to solve a problem based off this circuit is just finding its Q points, which is what you'll see in graphs, but um, we take an assumption that the first diode is on and then the second diode is off. So that means that this behaves as a singular voltage drop and this one behaves as an open circuit with the poles the terminals positive and negative here, positive and negative here. This is a voltage drop. This would be an open circuit. Um, to solve it, we would just use basic circuit analysis from 231. So let's define currents here. I1, I2, I3. You could think of the KCL as equal to I1 is equal to I2 plus I3. So how to find I1? Well, we just choose to have the voltage here, which is 6 volts, and the voltage here, which would be the voltage on the diode, which is 0.4 volts, as we stated in the beginning.
I'm
And then
sorry to interrupt, Sergio. I think,
yes.
is there something to the left of the multi-sim screen? Because it's just black on mine.
Can you guys not see? Okay.
I don't know if anybody else can see it, but I see
No,
the multi-sim screen, but I don't see what's.
This
yeah,
is weird.
Sergio. Instead of screen sharing multisim, screen
Yeah.
share like screen one or screen two, wherever you're at. Because
Oh, okay.
then you could then yeah, that works.
Oh my God. I am so sorry. Um,
Yeah, I was trying to figure out if you were pointing to something or were those your notes to the side the whole time, but
yeah,
yeah.
that's my fault. Okay. Let's restart. So, um, we'll skip the introduction and just go to like what the problem was. Um, so for this problem, we're looking at this circuit that we can see here of that came from the book. We're trying to find the voltages and currents uh, in the diodes. What we're given is the voltage drop across a diode, which would allow us to like see how much voltage drop it would have if it's on, or there's current going through its forward to in its forward active region. Um, Again, Levkov will go more with more examples in class, but this will be a simple one. So to continue solving analytically, we would see that the voltage drop or we take an assumption first, and we choose the diode states to either be on or off. So looking back at the previous figure, we see that the diode 2 is in this configuration and diode 1 is here, and on the cathode and on the cathode. So um, when there's current, we take an assumption that diode 1 is on and diode 2 is off. So there will be a voltage drop coming from D1, but no voltage drop, there will be current going through diode 1, but no current going through diode 2. So it behaves like an open circuit here. This behaves like a voltage drop, or in some cases of like just seeing a circuit analysis, is just like a voltage source. Um, but just to solve it mathematically and analytically and realistically in real life, it doesn't behave as a source of power. It consumes power. Diodes consume power. But we use it and we see it in this way aspect to analytically solve circuits like this. You guys can see, right? So, okay,
Yep, we see the presentation.
okay. So, um, to find the current going through, we can then continue into solving the circuit analytically uh, by using basic circuit analysis that we guys learned from 231. So to find between the current going through this branch, we would just take the voltage difference between this node and this, or this voltage point and then this voltage point. We chose the voltage drop across a diode, which is when it's on, is going to be 0.4. And here it's just 6 volts. And then it's going across a 43 kilo ohm resistor. From that, we just then get the current that's going through it is 0.13 milliamps. Now, one of the things that you should notice, since this diode here is off and behaves like an open circuit, no current is going to run from it. So I3 is automatically equals to 0, or it's always 0 when it's open, because open circuits have no current always running to it. That then tells us, or at least we continue in this assumption, I1 is equal to I2, and that means that there is current going through this diode, which you see it was in this configuration and allows voltage and current to go through, or voltage to be active here, a voltage drop be active here, and current running from top to bottom of that branch. But we can still find the voltage drop across this diode here, which is off. Now, a thing that should be known is that the voltage drop is going to be negative, or it's going to be always be less than 0, regardless. It can't be positive because that would mean that it's actually on. But if it's negative, it's always off. Now, depending on your labels too, that's an important thing also. So we take a KVL and we would just figure out what the voltage drop across this diode that's off is. So we take negative 0.4 from the terminal, then include negative VD2, and then add the 9 volts that are here. Again, no current is running through this resistor, so no voltage drop. So it just is 0 volts here. But you still have a voltage source here, which is significantly impacting the KVL. So when you go around the loop, then you include negative 9 volts. And then that is all equal to 0, as case KVLs are known to be. And then we can find that VD2 is equal to negative 9.4 in the terminal configuration that we have set here. So then we can find, or we can state the Q points on assumption 1, which proved to be true because D1 is on, there is a 0.4 voltage drop here, and D2 is off because the voltage drop across this diode that's off is less than 0 or it's negative. So we then state that Q point for D1 will have the current that's going through this diode and the voltage drop that you see across the diode terminals, which will be 0.4 and 0.13 milliamps. For D2, we then find that there's no current going through it and that the voltage drop or the voltage across the terminals in this configuration is equal to negative 9.4. This gives us enough information of the behavior that we expect in the circuit. Then we'll take that information we found out and apply it to our simulation assignment, or at least simulating it in Multisim. So constructing it, we'll have to then take also consideration that we will choose the virtual diode component. So now I'll move on to Multisim. You guys can see? Yes?
I just had a question.
Yes.
So when the diode is off, it's always going to have a current of 0, and the voltage will be always negative.
Depending on where it is, yes, there's no current running through it because it behaves like an open circuit. You basically like you cut like a wire, and there's no current being able to just run through it. So, but it's in this case, it's a diode that doesn't permit the current to run. That's how it behaves. If Levkov will lecture you probably sometime this week, he'll go more in depth of why, with how like a diode behaves. Also, it goes with the physics. If you guys were still remember that, it relates a lot to the physics, and you then look at them in like the behavior on a graph, which is helpful to also understand how the diodes behave. But yes, does that answer your question?
Yes.
Okay, so moving on, we will then simulate and put the circuit that we had from the slide here, this one right here, into Multisim. So the way you would set it up is it could be like this, or you could set it up in this this configuration or fashion. We choose voltage reference, and then we then choose a ground. We'll choose a ground here, right? Then we'll choose another voltage reference that is different from the other one that we know that we had here. And that's gonna be acting as our 9 volts here. So our negative 9 volts. So the voltage references can be found when you go into sources and you choose power sources. They should be here. They also has different ground references, but for the sake of just what you need to do in the simulation assignments, this is what you'll have to be using. But encouraged to like see how these different components behave when you include them in one circuit. So let's just flip this vertically. Now we need to choose a resistor. You just then go into, again, components here, and you'd say place basic. There are resistors here. And then we'll choose another one and then place it here. Now, for right now, I'm just choosing a random resistor, but you can always edit them. So you could always edit them to be 3 kilo ohms, 22 which are the 22 kiloohms, which are the values that we saw in that example or the diagram. Now, for finding our diodes, there's a special component, or at least symbol on the taskbar of Multisim that says place diode. Always go to virtual. Virtual in the sense of the Multisim definitions, basically ideal. It behaves like a perfect diode. In reality, no diode is perfect, and specifically any component in electronics is nowhere near perfect. In percentage wise, can be near, can be proportional, depends on different fields. In computers, it has to be really exact, but in, let's say, power, in the power industry, you don't need that much to have like perfection, because large numbers and different things that kind of behave in it. So we'll choose 2 diodes for the moment being to just then construct the circuit. Flip this and turn this clockwise. Okay. As of now, this is the same circuit. Oh, this one part was supposed to be 6 volts. So, as of now, this circuit here, in a sense, it's similar configuration as this one. Only difference is that this has obviously closed loops from these battery sources, which you could use. It's up to your comfortability as long as you're understanding the circuit and how it's behaving. Now, we know our values that we've calculated, or at least analytically solved from this part of the lecture. You know that these are the cue points that we're looking for, or at least the behaviors from the diodes. To find those, we have to place probes. Probes are usually here in these icons. So these are the voltage probes, behave like voltmeters, and these are the current probes, which behave like ammeters. Now it depends how you use these. How you use these depend also on the type of simulation you'll do. I'll get onto that a bit later. Just do that. And we also want to see the current going through this one, current going to this one, and no, we don't need the voltage here. Yeah, right. Do that. Okay. We don't need that. We only need also the current going through this branch. So, that's what we're really mainly looking for. And also, actually, no, we need the voltage drop across this diode. Okay. Similar fashion, how we see this circuit is the same configuration here. Now, simulating is the same way how it would behave. Now, also check on your circuit and just seeing that it's how you have it set. Initial device voltage, that allows you to choose what you well, the moment you would have to go to edit model, and you would have to find your voltage drop. Should be somewhere here. No. Potential. Okay. No. Oh no. Yeah. Okay. So here is where your voltage is across your diode that you choose to be your voltage drop. So choose it to be this. So once there's current running through it, it will have a voltage drop of 0.4 volts. Now, we should be ready to simulate this. And to simulate it, you press click, or just go into just a quick mention. You'll use different types of simulation and types of analysis that Multisim does. The different types of functions and ways you look at a circuit. For now, interactive is basically live feed, which lets you see a circuit on live time instead of like other ones like transient would just give you the behavior on a graph and won't be simulating the circuit on live time. It's like a short time span that you gave it to just be watching the circuit and automatically gives you the behavior. But for now, in the case of this simulation assignment, you're only looking to do the interactive simulation. And time stop basically means the time that if you leave this on your computer for like however long overnight, it's going to stop after this certain amount of seconds. And initial conditions usually have them set as determined automatically. But this is important just to know, so then if you accidentally make a mistake in how you have it configured, you can go back and find out what was the issue that's kind of stumping your simulation progress. But let's continue with the interactive simulation. And we will be able to see now the behavior of the circuit. Similar to how it's done this one on the left, same behavior, right? We have a voltage drop of 0.6 volts and a current of 126 milliamps. Even though we have it set to have this voltage drop of 0.4, diodes behave differently because of just nonlinear behavior. So this is kind of odd because we found out from our calculations this is supposed to be the voltage drop you see in this diode here, but we're getting 0.6. Same thing with the current. The current is not what we calculated. It's supposed to be 0.13 milliamps, but we're getting something else. We're getting a different current. So same thing with the voltage drop across this diode. Not the same thing. It's negative 9.6. This is supposed to be negative 9.4. So let's move on. And so what is the issue with this? Diodes are not linear circuits, and we have to use a formula to find that the current that's going through the diode. You guys might have not seen it yet, or might have just peeked it at on the lecture notes. This is how it's set. The diode current the current that's going through the diode is dependent on a saturated current value multiplied by an exponential of the voltage drop across the diode that is in the diode over a nominal factor multiplied by voltage, natural voltage drop in room temperature of semiconductor. And that entirely is subtracted by 1 and then close parentheses, and that's multiplied to the saturated current. Saturated current is something that you decide in industry of what your how you want your diode to behave. So we'll continue to expand that, and then we already chose that how we want this voltage drop to be 0.4 and the current going through it to this diode to be 0.13 milliamps. We'll choose that in this equation, and then we're just gonna have to find our saturated current, which is a variable that can be played around with in the model of this diode, this virtual diode. You can edit them in Multisim. So this is the saturation current, which is chosen by industry. So we want to choose this current for the current seen by the diode, and this voltage to be the voltage drop across the diode. And additionally, we already know that Vt is equal to 0.025 volts. And let's just assume that the nominal factor is equal to 1. We'll, after calculating this by just doing algebra, so like this Is is equal to Id over this entire exponential minus 1, we will get 1.4 times 10 to the negative 11th amps. Now, this is going to be plugged into Multisim. So we're going to put 1 46557. That's pretty good. We're fine. So we choose that, and then change all 4 components, because that means all the virtual diodes will be affected with this value. So let's just do that. Simulation is running, but that doesn't matter. We'll just end it, and then we'll then choose to have run this simulation again. Now all the diodes have this chosen saturation current, and we will now just run it again. See what's the behavior. Cool. This is nearby almost exactly to what we calculated to. We got the correct current, sort of not the same voltage drop that we were given and chose for this diode to have, and sort of the same thing for the voltage drop or the voltage across this diode when it's off. Now that's an odd thing because it should be accurate. This is a part of a diode that makes it a nonlinear component. It is not to the exact values, so then you have to kind of play about with the factors that you have. So let's just see. The only variable that we can play around or that affects the diode's behavior is the saturation current. So let's just play around and see where if we increase it or decrease this value here comes to our favor of what we already calculated or expect to be. So we will then just play around with this. Let's just say, let's increase it to 2.0. So we're increasing the current that is in the saturation current of all the diodes. So let's just see. Stop the simulation, run again. This is getting closer. Same current that we expected and calculated. Same thing with the voltage drop or the voltage across this diode that's off. It's still close, but let's see how far we have to increase it. So let's just go with 2.2, or let's just go with 2.5 already. Reason why is because that's actually what's gonna help our diode to behave like how we calculate it to be. So, or at least to an extent similar to what we expected. So it's changed. Yes. Okay. And there, our circuit is showing the values that we calculated and expect this diode to behave like. And that is because we changed the saturation current to be of this value, 2.5 times 10 to the negative 11. You don't need to remember it, you just need to understand that saturation current affects the diode's behavior. And even if you calculate it by doing the calculations, it's still not exact to actually get you the correct behavior of the circuit. So you have to just fiddle around with the diode's characteristics, because that's what in industry you do. You kind of have to choose the best characteristics that give you the best outcome of behavior. And that's basically what you do, or you'll be doing in the simulation. You're trying to find if what you calculated in analytical would behave the same way or give you the same answers as if you would do it by a simulation. And the answer would be sort of, or at least to some extent sort of, because just a diode is a nonlinear component. Doesn't behave like as a resistor, an inductor, or a capacitor where you could just, the value of the component. But here it's like you gotta just plug and play and figure it out from knowledge that you did that does follow the logic of circuits. And that's basically how you find and simulate these behaviors of diodes or a diode circuit. Does anybody have any questions regarding what has happened, anything with diodes that I just demonstrated?
Can you go back to your slide 5?
Yes.
I think I'm not fully sure what all the variables like mean. Like ID, is that just saturated current, or like do you mind explaining what each one of those means?
So ID is your current that is observed by the diode, or it's going through the diode. Saturation current a is a variable that is part with what the diode comes with when it's manufactured. It's part of its characteristic. So like it's something that like um is just chosen in industry to have its behavior to be like. Same thing like the voltage drop that you want to see across the diode. That's something chosen by industry. Um, and but saturation current is kind of like you have to play about with the variable because it doesn't always. It's like it's something that's chosen by industry to like be part of the diode when it's manufactured. Um, Lavkov will go into better explanation since he'll show with graphs, and you also learn about voltage transfer characteristics because that also relates to this. Um, and basically, this is the current going to the diode. This is the current with the that's chosen with the diode, and this is the voltage that's chosen for the diode's voltage drop. This would be the voltage that is observed in semiconductors at room temperature, VT, at 0.025. Um, yeah, does that answer your question?
I think I got that. So ID is current going through diode. IS current chosen for diode.
Yes,
VD is voltage chosen for diode.
correct.
And I'm just write that because I didn't get the phone. And then N times VT is the chosen temperature. All I got was like chosen temperature. Wait, what was that one again?
So VT is the voltage um, that is observed in semiconductors at room temperature. So I forgot what the term is like. But basically, it's like at room temperature, it's a voltage that's relative to semiconductors. So um, it's like it's just natural that this voltage occurs at room temperature. Um, so I think it's terminal voltage, if I'm not wrong. No, that's a different thing. Um, but N is just a nominal factor that kind of like plays around with how this like exponential behaves with the diode voltage that you chose. Um, there's another variable that you could play around with in Multisim. So just go into this diode's model. I could then choose, where is it? Somewhere here. Somewhere here, there's a factor you could choose that usually just allows you to play around with it. And I think there's a Multisim has different symbols for it, but this might be it. It's chosen to be one in this case. Um, and I think that might be it. It's just some Multisim uses different symbols for other things. Conveniently, it does use it IS for saturation current, but other things which you would expect, especially for when you get into transistors, it's a different like symbol that it's not the same from the book or lecture slides. Um, but it's part of the formula just to like compensate for any irregularities. Um, does that help clear up stuff?
Yep, that works. I wasn't sure what any of those really meant, but yep, thanks.
Okay. You will go over this in class, hopefully soon. So this is kind of an introduction to multisim before you kind of get to fully understand diode circuits, but it's an introduction to it. Does anybody have any other questions?
Are these slides available
I
anywhere?
could actually make them available if you would like. I'll make sure to post these with the recording.
Okay, thanks.
Yes. Um, any other questions?
Where's that getting posted to again?
So if you are part of the IEEE Discord, or I'll make them also available or send them to Dr. Levkov so he can put them out for you guys' convenience. That's what I'll do. The IEEE Discord, it should announce if are you guys part of it or have you guys joined the Discord so at least you guys see any announcements for further workshops.
Yeah.
Yeah, so you will see an announcement hopefully later by today of the recording of this lecture and additionally with the lecture slides or workshop slides. Does anybody else have any other questions?
My bad, it just has like the third one. Can you send me the Discord link? I'm on the electrical engineering Discord. I don't know if that's the same thing.
Yeah, that's the NCE one, right?
NCE, yeah.
Check if this works. Wait, this is the Discord. Give me a second. So weird. It's being weird. I don't know. Check if this works. If not, I'll put in also. Have you guys gotten that flyer that was advertising the workshop? If you guys saw it from Levkov's announcement, at least there.
A student sent it to me. That's where I saw it. I think he found it on like the announcements of the NCE Discord.
Yeah, so okay, you can actually see it on the NC. So if you see on the announcement or club announcements of the NC Discord, you should see a join our Discord QR code. And if you scan that, that should allow you to then join the Discord server for IEEE. And there you get more direct announcements for any upcoming um, workshops and in this case, the recording of this workshop that we just did and this lecture slides. Okay. So I will stop the sharing. Any other questions? If not, then this would conclude the workshop. And if you are part of the 232, you could stick around and wait for the second simulation workshop for 232. And if not, you should be free to leave. And yeah, I'll make sure to post these on the IEEE Discord and make an announcement on the NCE Discord so then everybody gets their or at least aware that these recordings are available for you guys. All right. Thank you all for coming. If you're leaving, for anybody that stays, then just hold up and we'll wait for any more people.